Welcome to Alien Nature for Sleep, where we explore the most extraordinary corners of our universe through a lens of calm wonder and scientific discovery. Tonight, we journey to the coldest places in existence beyond Earth. Places where temperatures plunge to depths that challenge our understanding of matter itself. Where frozen worlds drift through the darkness of space, their surfaces coated in exotic ices that would shatter like glass beneath your touch. Where atmospheres, if they exist at all, hang heavy with compounds that exist nowhere else in forms we recognize. These are not the fiery giants we often imagine when we think of distant worlds. These are planets and planetary bodies that have surrendered to the absolute cold of the cosmos, where starlight arrives too weak to warm their surfaces, where internal heat has long since radiated away into the void, leaving behind landscapes of stillness and silence. They are worlds where nitrogen freezes solid, where methane becomes ice as hard as rock, where even the faint glow of distant suns cannot penetrate the perpetual twilight. Understanding cold in the universe. Before we visit these frozen realms, we must first understand what cold truly means in the context of space. On Earth, we experience cold as the absence of heat, a sensation that arises when thermal energy drains from our bodies faster than we can generate it. But in the universe, cold takes on a more fundamental meaning. It represents the state of matter when molecular motion slows to its minimum possible level, when atoms vibrate with barely enough energy to maintain their quantum existence. Temperature, at its core, measures the average kinetic energy of particles within a substance. The hotter something is, the faster its molecules move, colliding with one another in chaotic dance. The colder something becomes, the slower these movements grow, until at the theoretical limit called absolute zero, minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit, or 0 Kelvin, particles would reach their lowest possible energy state. At this point, not even quantum mechanics allows them to stop moving entirely. They retain what physicists call zero-point energy, a residual vibration mandated by the fundamental uncertainty of nature itself. No place in the natural universe has ever reached absolute zero. Even the coldest regions of space, far from any star, maintain temperatures of about 2.7 Kelvin, warmed by the cosmic microwave background radiation, the fatting afterglow of the Big Bang itself. This ancient light, stretched and cooled by billions of years of cosmic expansion, bathes all of space in a faint warmth that prevents anything from cooling below this threshold naturally. Yet some planetary bodies come remarkably close to this limit, their surfaces hovering just tens or hundreds of degrees above absolute zero. The planets we will encounter tonight exist in temperature regimes that would be unrecognizable to any Earth-dwelling organism. Water, the liquid medium of all known life, becomes as solid and unyielding as granite. Carbon dioxide, which we exhale with every breath, forms dry ice that never melts, sublimating directly from solid to gas if enough energy arrives. Nitrogen, which comprises most of Earth's atmosphere, freezes into crystalline solids. Methane, a gas on Earth, becomes an ice harder than many rocks. These worlds challenge our Earth-centered intuitions about what planets should be, expanding our understanding of the diversity possible in planetary systems across the galaxy. Scientists measure temperature in several scales, each with its own historical context. The Celsius scale, used widely in science and daily life outside the United States, sets the freezing point of water at 0 degrees and its boiling point at 100 degrees under standard atmospheric pressure. The Fahrenheit scale, still common in the United States, places water's freezing point at 32 degrees and its boiling point at 212 degrees. But for the extreme temperatures we will encounter tonight, the Kelvin scale proves most useful. It begins at absolute zero and progresses upward without negative numbers, making it ideal for describing phenomena at the coldest extremes of existence. When we speak of planets with temperatures of 50 Kelvin, we describe worlds where the air itself would freeze and fall as snow. At temperatures of 100 Kelvin, substances that are gases on Earth solidify into exotic ices. At 200 Kelvin, we approach temperatures where liquid water could theoretically exist, though on most of these worlds, water has long since frozen solid or never existed in significant quantities to begin with. Each degree on this scale represents a fundamental shift in the behavior of matter, a transformation in how molecules interact, how energy flows, and how the physical world manifests itself. The coldest planets form through various mechanisms, but they share common characteristics. Most orbit their stars at tremendous distances, far beyond the region where stellar radiation could provide meaningful warmth. Some orbit dim red dwarf stars that emit a fraction of the energy produced by our sun. Others have been ejected from their planetary systems entirely, wandering through interstellar space without any star to call home. Still others orbit the remnants of dead stars, white dwarfs or neutron stars, that have exhausted their nuclear fuel and cooled over billions of years. Distance from a star represents the primary factor determining a planet's temperature. In our own solar system, we observe this principle clearly. Mercury, closest to the Sun, experiences surface temperatures that can reach 430 degrees Celsius on its day side. Earth, at a moderate distance, maintains temperatures suitable for liquid water and life. The outer planets, Jupiter, Saturn, Uranus, and Neptune, receive far less solar energy per unit area, maintaining much colder environments. Beyond Neptune, in the realm of dwarf planets and other trans-Neptunian objects, temperatures plunge even further. Pluto, orbiting at an average distance of 5.9 billion kilometers from the Sun, experiences surface temperatures around -230 degrees Celsius, cold enough to freeze nitrogen and methane solid. But some planets exist in even more extreme environments. Imagine a world orbiting so far from its star that sunlight arrives as little more than starlight, too dim to read by, too weak to cast shadows. Imagine a planet whose year lasts decades or centuries, its orbit carrying it through the outer darkness of its planetary system. Imagine a world that formed around a star that later died, leaving behind only a cooling ember that provides no warmth at all. These scenarios produce planets colder than any in our solar system, worlds where the laws of thermodynamics play out in their most extreme form. The study of cold planets reveals fundamental truths about planetary formation and evolution. By examining these frozen worlds, astronomers gain insights into how planetary atmospheres behave under extreme conditions, how surface processes operate without liquid water, how geology manifests on bodies where volatiles behave entirely differently than on Earth. Each discovery adds another data point to our growing understanding of planetary diversity, showing that the warm, water-rich world we call home represents just one possibility among countless variations nature has produced. As we begin our tour of the coldest known planets, prepare to encounter environments unlike anything in human experience. We will visit gas giants so cold their atmospheres contain ices of water and ammonia. We will explore rocky worlds where the surface temperature hovers just above absolute zero, where any atmosphere has long since frozen and fallen to the ground. We will meet rogue planets drifting alone through the galaxy, their surfaces lit only by the faint glow of distant stars. And we will contemplate brown dwarfs, objects that blur the boundary between planet and star, whose temperatures barely exceed those of our own temperate Earth. These worlds exist not in imagination, but in reality, detected by the careful observations of astronomers using the most sophisticated instruments humanity has ever built. Some were discovered through the wobble they induce in their parent stars. Others revealed themselves through the brief dimming of starlight as they passed in front of their suns. Still others were found through gravitational lensing, where their mass bent and magnified the light of more distant stars. Each detection represents a triumph of human ingenuity, a testament to our species' drive to understand the universe beyond our small blue world. WD 1856 plus 534b, the coldest exoplanet ever confirmed. In the vast catalog of exoplanets discovered over the past 3 decades, one world stands apart as the coldest planetary body ever directly observed beyond our solar system. This planet, designated WD 1856 plus 534b, exists in an environment so frigid that it challenges our understanding of how planets can survive in such extreme conditions. With an average atmospheric temperature of approximately minus 125 degrees Fahrenheit, or minus 87 degrees Celsius, or 186 Kelvin, this gas giant represents the current record holder for the coldest confirmed exoplanet. WD 1856 plus 534b was first discovered in 2020 during observations that identified it as a transiting planet, a world that passes in front of its star as seen from Earth, causing periodic dimming of the star's light. The discovery itself was remarkable, as this planet orbits not a normal main sequence star like our Sun, but rather a white dwarf, the dense remnant core of a star that long ago exhausted its nuclear fuel and collapsed to roughly the size of Earth while maintaining a substantial fraction of its original mass. White dwarfs represent the final evolutionary stage for stars similar to our Sun. After billions of years of fusing hydrogen into helium in their cores, these stars eventually exhaust their fuel supply. The outer layers expand dramatically, forming a red giant that may engulf any inner planets. Eventually, these outer layers drift away into space, leaving behind the compressed, super-hot core. Over millions and billions of years, this core gradually radiates away its stored thermal energy, cooling from temperatures exceeding 100,000 Kelvin to mere thousands of degrees. The white dwarf that WD 1856 plus 534b orbits has cooled considerably from its formation, but it still provides a unique environment for planetary study. The planet itself possesses remarkable characteristics. With a mass approximately 6 times that of Jupiter, WD 1856 plus 534b qualifies as a super-Jupiter, a gas giant substantially more massive than the largest planet in our own solar system. Jupiter itself has a mass 318 times that of Earth, making WD 1856 plus 534 be nearly 2,000 times more massive than our home world. Despite this enormous mass, the planet orbits its white dwarf host very closely, completing one full revolution every 1.4 Earth days. This proximity to its star makes its extreme cold even more puzzling at first consideration. One might expect that a planet orbiting so close to any star would be intensely hot, heated by the radiation from its host. Indeed, most close-orbiting exoplanets discovered to date are so-called hot Jupiters, gas giants that have migrated inward from their formation locations and now experience temperatures of thousands of degrees Celsius. Their atmospheres seethe with exotic chemistry, their dayside hemispheres potentially hosting clouds of vaporized rock or iron. WD 1856 plus 534b could hardly be more different. Its white dwarf host, while still warm by terrestrial standards, emits far less total energy than an active main sequence star. The low luminosity of white dwarfs means that even planets orbiting close to them receive relatively little heating. This property of white dwarfs opens a unique window for astronomers studying cold planetary atmospheres. Under normal circumstances, directly observing the light from an exoplanet proves extraordinarily difficult. The overwhelming brightness of the parent star drowns out the faint reflection or thermal emission from the planet itself. This contrast challenge has limited direct atmospheric characterization to a small subset of exoplanets, typically young, massive, and very hot worlds that emit substantial infrared radiation. But white dwarfs, being small and dim compared to main sequence stars, create far less contrast between themselves and any orbiting planets. This reduced contrast made WD 1856 plus 534b an ideal target for detailed study with the James Webb Space Telescope. Observations with JWST's mid-infrared instrument in 2024, with results published in early 2025, successfully detected thermal emission directly from WD 1856 plus 534b, confirming its existence as a planet rather than a brown dwarf, a distinction that had remained uncertain based on earlier observations. The spectrum of light from the planet revealed its temperature distribution and provided constraints on its mass. The measurements confirmed the planet's frigid state, with average temperatures of 186 Kelvin, making it colder than any planet with directly measured thermal emission had ever been observed. To put this temperature in perspective, consider that 186 Kelvin equals minus 87 degrees Celsius, or minus 125 degrees Fahrenheit. At this temperature, carbon dioxide, a gas in Earth's atmosphere, would freeze solid immediately. Water ice would be as hard as granite. If Earth were somehow cooled to this temperature, our oceans would freeze completely solid. The atmosphere would collapse and snow down onto the surface, leaving only the most volatile elements, suggesting a profoundly transformed world where familiar processes cease entirely. The planet experiences temperatures well below the coldest natural temperature ever recorded on Earth, which was minus 89.2 degrees Celsius at Vostok Station in Antarctica. The atmosphere of WD 1856 plus 534b likely contains compounds common to gas giants, hydrogen and helium forming the bulk composition, with traces of methane, ammonia, water vapor, and other molecules mixed in. Based on the planet's extreme temperatures, many of these compounds would exist near their condensation points, where they transition between gas and solid or liquid phases. This could create a complex atmospheric structure where different layers may host different types of clouds or hazes. Water might form ice clouds similar to cirrus clouds on Earth, though at pressures and temperatures that would produce exotic ice phases, unlike anything found in terrestrial experience. The discovery of such a cold planet orbiting a white dwarf has profound implications for understanding planetary system evolution. The planet's current orbit likely differs substantially from its formation location. When the star that became the white dwarf entered its red giant phase, it would have expanded dramatically, potentially engulfing the planet's original orbit. How WD 1856 plus 534b survived this phase and ended up in its current close orbit remains a subject of ongoing research. Perhaps it migrated inward after the red giant phase concluded, pulled by gravitational interactions with other planets in the system. Perhaps it formed farther out and later moved inward. Each scenario provides different insights into how planetary systems respond to stellar evolution. WD 1856 plus 534b also offers a preview of what might happen to planets in our own solar system billions of years in the future. Our sun will eventually exhaust its hydrogen fuel and expand into a red giant, likely consuming Mercury, Venus, and possibly Earth. The outer planets, Jupiter, Saturn, Uranus, and Neptune, may survive, their orbits potentially perturbed by the mass loss as the sun sheds its outer layers. Eventually, the sun will become a white dwarf, gradually cooling over trillions of years. Any surviving planets will orbit this cooling ember, their temperatures dropping as their star fades. Studying systems like WD 1856 plus 534 provides a window into this distant future. The planet's extreme cold also makes it an excellent laboratory for studying atmospheric chemistry under conditions rarely encountered. Most exoplanets studied to date either orbit very close to their stars and experience intense heating, or orbit far enough away that they remain too dim for detailed observation. WD 1856 plus 534b occupies a unique middle ground, close enough to be observable, yet cold enough to display chemistry and physics unlike anything seen on hot Jupiters. Future observations with JWST and other next-generation telescopes will probe its atmosphere in greater detail, searching for specific molecules, characterizing cloud structures, and measuring how temperature varies with altitude and location on the planet. Scientists hope to use these observations to test theoretical models of giant planet atmospheres. Computer simulations predict how gases should behave under various conditions, how clouds should form and dissipate, how energy should flow through different atmospheric layers. By comparing these predictions to actual observations of WD 1856 plus 534b, astronomers can refine their models, improving our understanding not just of this particular planet, but of gas giants throughout the galaxy. The knowledge gained will help interpret future observations of similar worlds and may even provide insights relevant to understanding the ice giants of our own solar system. The mere existence of WD 1856 plus 534b challenges some theoretical expectations. Before its discovery, it was unclear whether planets could survive the tumultuous evolution of their host, star, through the red giant phase into the white dwarf stage. The detection of this world proves that such survival is possible, opening the possibility that white dwarf systems may commonly host planets. Given that most stars in the galaxy will eventually become white dwarfs, this suggests that planetary systems might persist far longer than the main sequence lifetimes of their stars, potentially providing stable environments for billions or even trillions of years as their stars slowly cool. WD 1856 plus 534b will continue to cool over time as its white dwarf host gradually radiates away its remaining thermal energy. Billions of years from now, this world will be even colder than it is today, potentially approaching temperatures only tens of degrees above absolute zero. At such extreme cold, the atmosphere's behavior would change dramatically. Gases that currently remain airborne might freeze and fall to the surface. Cloud layers would restructure. The planet would become even more of an ice world, though still retaining its massive gaseous envelope. For now, WD 1856 plus 534b holds the record as the coldest exoplanet with directly measured atmospheric properties. This distinction may not last forever. Future observations with more sensitive instruments may reveal even colder worlds, perhaps gas giants orbiting more distant white dwarfs, or rogue planets drifting through interstellar space without any star at all. But for the present moment, this frigid super-Jupiter represents the extreme end of planetary temperatures that we can observe and characterize in detail, offering a glimpse of worlds fundamentally different from anything in our solar system. The planet reminds us that the universe contains endless variety, that planets come in forms barely imagined when exoplanet searches began just a few decades ago. Each new discovery expands our catalog of possible worlds. Each observation refines our understanding of planetary processes, and each measurement brings us closer to answering fundamental questions about how planets form, evolve, and perhaps even host life under conditions we might never have anticipated. WD 1856 plus 534b, frozen in its eternal orbit around a dying star, stands as testament to the resilience of planets and the diversity of environments the cosmos has produced. Epsilon Indi Ab and other cold gas giants. While WD 1856 plus 534b holds the record for the coldest exoplanet with directly measured atmospheric properties, several other distant worlds compete for similar distinction, each revealing unique aspects of planetary science in cold environments. Among the most remarkable of these is Epsilon Indi Ab, a gas giant discovered in 2024 that represents one of the coldest exoplanets ever directly imaged, with an estimated temperature of just 35 degrees Fahrenheit, or 2 degrees Celsius, barely above the freezing point of water. Epsilon Indi Ab orbits a star known as Epsilon Indi A, located approximately 12 light-years from Earth in the southern constellation Indus. This makes it one of the closest exoplanets to our solar system discovered to date, the 12th closest known exoplanet, and the closest planet more massive than Jupiter. The host star itself is a K-type main sequence star, slightly cooler and less massive than our Sun, with an age comparable to our own star's 4.6 billion years. This relative proximity and the planet's unusual properties make it an exceptionally valuable target for detailed study. The planet was discovered using the direct imaging technique, where powerful telescopes equipped with coronagraphs, devices that block the overwhelming light of the host star, detect the faint light emitted or reflected by the planet itself. Direct imaging remains one of the most challenging methods for discovering exoplanets, requiring extraordinarily precise optics and sophisticated image processing to separate planetary light from stellar glare. Of the thousands of confirmed exoplanets, only a few dozen have been directly imaged, most of them young, massive, and hot enough to emit substantial infrared radiation. Epsilon Indi Ab breaks this mold entirely. The planet's discovery came through observations with the James Webb Space Telescope's mid-infrared instrument, which possesses sensitivity unprecedented in the history of astronomy. The coronagraph on MIRI blocked most of the star's light, allowing the telescope to detect the faint infrared glow of the planet itself. What emerged from the data was remarkable. A world with surface temperatures cooler than any other imaged exoplanet beyond our solar system, and even colder than all but one free-floating brown dwarf. At just 2 degrees Celsius, or 35 degrees Fahrenheit, Epsilon Indi Ab maintains temperatures barely different from a cool spring day on Earth. Yet this relatively mild temperature exists on a world completely unlike our planet. The exoplanet is several times more massive than Jupiter, classifying it as a super-Jupiter or possibly a brown dwarf, depending on precise mass determinations that remain somewhat uncertain. It orbits its star at a considerable distance, taking many Earth years to complete a single revolution. This distant orbit, combined with the dimmer nature of its K-type star, creates an environment where very little stellar heating occurs. The similarity in temperature between Epsilon Indi Ab and Jupiter itself, which maintains a temperature around -145 degrees Celsius at its cloud tops, though the top of its atmosphere where less is known might be warmer, provides a unique opportunity for comparative planetology. For the first time, astronomers can compare a Jupiter analog in another solar system directly with our own gas giants, examining how atmospheric composition and structure vary or remain similar across different planetary systems. This comparison helps constrain models of giant planet formation and evolution, testing whether Jupiter represents a typical outcome of planetary formation or an unusual case. Early spectroscopic observations of Epsilon Indi Ab will focus on detecting specific molecules in its atmosphere. Scientists expect to find methane, water vapor, and ammonia, compounds common in giant planet atmospheres. The exact abundances of these molecules will reveal information about the planet's formation history and chemical evolution. If methane is depleted relative to solar abundances, it might indicate photochemical processes breaking it down in the upper atmosphere. If water is enriched, it could suggest formation in a region of the protoplanetary disk where ice was particularly abundant. Another cold gas giant recently identified is 14 Hercules c, announced in June 2025 based on JWST observations. This massive world, about 7 times the mass of Jupiter, maintains a surface temperature of just 26 degrees Fahrenheit, or -3 degrees Celsius, cold enough to freeze water solid, yet warm compared to most planets discussed tonight. What makes 14 Hercules c particularly interesting is not just its temperature, but its orbital configuration. The planet follows a tilted orbit relative to another planet in the same system, creating a dynamically complex environment where gravitational interactions between the worlds shape their long-term evolution. 14 Hercules c orbits a sun-like star approximately 60 light-years from Earth. The star's similarity to our Sun makes this system especially valuable for comparison with our own solar system. The planet's discovery through direct imaging with JWST marked a breakthrough in observational capability. Previous instruments could not detect worlds this cold through direct imaging. The ability to see and characterize such planets opens new frontiers in exoplanet science, potentially allowing the detection and study of gas giants similar to Saturn and Uranus in other solar systems. The coldness of these planets arises from their orbital distances and the energy output of their host stars. Unlike hot Jupiters, which orbit so close to their stars that they experience temperatures exceeding 1,000 degrees Celsius, cold gas giants like Epsilon Indi Ab and 14 Hercules c orbit at distances where solar heating is minimal. They receive only a fraction of the energy that Earth gets from the sun. At these distances, the primary energy source for the planet comes not from stellar radiation, but from internal heat, the residual warmth from the planet's formation, and the slow gravitational contraction that continues throughout a gas giant's lifetime. All gas giants generate internal heat through this gravitational contraction. As the planet very slowly shrinks under its own weight, gravitational potential energy converts to thermal energy, warming the interior and causing the planet to emit more energy than it receives from its star. Jupiter, for instance, radiates about 1.7 times as much energy as it absorbs from the sun. Saturn exhibits an even higher ratio of about 2.5. Neptune, surprisingly, emits the most internal heat relative to absorbed solar energy of any planet in our solar system, with a ratio around 2.6, despite being the farthest planet from the sun. This internal heat generation means that gas giants never reach the true equilibrium temperatures they would if they merely absorbed and re-radiated stellar energy. Instead, they maintain temperatures somewhat higher than their distances from their stars would suggest. For planets like Epsilon Indi Ab orbiting at substantial distances, this internal heat represents the dominant energy source, far exceeding the meager solar energy that reaches them. The planet essentially acts as a very slowly cooling ball of gas, radiating its formation energy away over billions of years. The atmospheres of these cold gas giants exhibit complex structure and chemistry. Unlike Earth's atmosphere, which thins gradually with altitude until space begins, gas giant atmospheres possess no solid surface. Instead, atmospheric pressure and temperature increase continuously with depth, eventually reaching levels where hydrogen, the dominant atmospheric component, behaves more like a liquid than a gas. Deeper still, Pressure becomes so extreme that hydrogen enters an exotic metallic phase, able to conduct electricity like a metal despite being composed of the lightest element. Cloud layers form at different altitudes based on the condensation temperatures of various compounds. On Jupiter, ammonia ice clouds form in the upper atmosphere, where temperatures drop to around -150 degrees Celsius. Deeper down, where it's warmer, clouds of ammonium hydrosulfide might exist. Even deeper, water ice or water droplet clouds could form. Each layer reflects different wavelengths of light, creating the banded appearance we observe in Jupiter's atmosphere. Similar processes likely occur on Epsilon Indi Ab and other cold gas giants, though the exact composition and structure of their cloud decks remains to be determined through future observations. The coldest gas giants also experience weather patterns driven by heat transport and rotation. On Jupiter, jet streams circle the planet at different latitudes, creating the famous banded structure visible in amateur telescopes. The Great Red Spot, a persistent anticyclonic storm larger than Earth, has raged for at least centuries and possibly much longer. Neptune exhibits even more vigorous weather, with wind speeds reaching 1,500 miles per hour, the fastest winds recorded on any planet in our solar system. These winds arise from the interplay of internal heat and the planet's rotation, creating atmospheric dynamics that remain incompletely understood even for our nearby gas giants. Understanding cold gas giants like Epsilon Indi Ab helps astronomers predict conditions on similar planets throughout the galaxy. Statistical studies suggest that most planetary systems likely contain at least one gas or ice giant. If these giants typically form in the outer regions of their systems where temperatures are low, then cold gas giants may actually be far more common than the hot Jupiters that dominated early exoplanet discoveries. These cooler worlds, however, remain much harder to detect, requiring either decades-long observations of stellar wobbles or the extraordinary sensitivity of instruments like JWST for direct imaging. The detection of these cold worlds also has implications for the search for habitable planets. While gas giants themselves seem unlikely to host life, they lack solid surfaces and experience crushing pressures in their deep atmospheres. Their moons might offer more hospitable environments. In our solar system, several moons of Jupiter and Saturn show evidence of subsurface oceans that could potentially harbor life. Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, both appear to have liquid water oceans beneath their icy crusts, warmed by tidal heating from their host planet's gravity. If similar moons orbit the cold gas giants being discovered around other stars, they too might possess the ingredients necessary for life. Future observations will continue to characterize these frigid worlds in greater detail. Astronomers plan to measure their atmospheric compositions precisely, determine whether clouds exist and at what altitudes, study how atmospheric temperature varies with location and altitude, and perhaps even detect whether patterns or seasonal variations. Each piece of information adds to our understanding of how planets work under conditions different from Earth, building a comprehensive picture of planetary diversity across the galaxy. These cold gas giants represent a bridge between the worlds we can study in detail in our own solar system and the vast number of exoplanets throughout the galaxy. They are close enough and bright enough to observe with current technology, yet distant enough to exist in truly alien environments. They expand our catalog of known planetary types and challenge theories of planetary formation and evolution. And they remind us that in the cosmic inventory of worlds, cold gas giants drifting through the outer darkness of their planetary systems may be among the most common destinations of all. Ogle 2000 5BLG 390 LB, the frozen super-Earth nicknamed Hoth. Far beyond the realm of gas giants lies a different class of cold world, rocky planets that experience temperatures so extreme they challenge our understanding of terrestrial planet formation. Among these frozen worlds, one stands out both for its remarkable coldness and for the elegant method by which it was discovered. This planet, designated Ogle 2000 5BLG 390 LB, but affectionately nicknamed Hoth by NASA scientists in reference to the ice planet from Star Wars, maintains surface temperatures around 50 Kelvin, or minus 220 degrees Celsius, or minus 370 degrees Fahrenheit. To understand just how cold this temperature is, consider that it lies only 50 degrees above absolute zero, the theoretical limit where molecular motion nearly ceases. At this temperature, the warmest regions of the planet would be colder than anywhere humanity has ever directly measured in the universe, except under laboratory conditions. Liquid nitrogen, used to freeze biological samples and achieve superconductivity in some materials, boils at 77 Kelvin, significantly warmer than Ogle 2000 5BLG 390 LB's surface. The planet exists in a temperature regime where exotic forms of matter manifest, where the few gases that remain unfrozen behave in ways unknown on Earth. Ogle 2000 5BLG 390 LB was discovered in January 2006 through a detection technique unlike any other commonly used in exoplanet searches. Rather than measuring stellar wobbles caused by an orbiting planet's gravity, or detecting the dimming of starlight as a planet passes in front of its star, this discovery employed gravitational microlensing, a method predicted by Einstein's general theory of relativity that uses the warping of spacetime itself to reveal the presence of distant worlds. Gravitational lensing occurs when a massive object passes between a distant light source and an observer. The object's gravity bends the fabric of spacetime around it, acting as a lens that magnifies and brightens the light from the background source. For stars in our galaxy, microlensing events are relatively rare, occurring when one star passes nearly directly in front of another from our perspective. The foreground star's gravity temporarily magnifies the background star's light over a period of days or weeks. But if the foreground star hosts a planet, that planet's additional gravity creates a characteristic spike in the light curve, a brief, sharp increase in brightness lasting hours that reveals the planet's presence and allows astronomers to calculate its mass and orbital distance. The discovery of Ogle 2000 5BLG 390 LB resulted from a collaborative effort among three major microlensing survey projects. The Optical Gravitational Lensing Experiment, OGLE, based in Poland, the Microlensing Observations in Astrophysics, MOA project led by Japan and New Zealand, and the Probing Lensing Anomalies NE-Twerk/Robotic Telescope Network, Planet/RoboNet, an international collaboration. These teams monitor millions of stars in the densely packed region near the center of our galaxy, watching for the telltale brightening that indicates a microlensing event in progress. On August 10, 2005, OGLE detected unusual brightening in a star designated Ogle 2005 BLG 390L. The planet team immediately began intensive follow-up observations using a network of telescopes spread across the globe, including a Danish telescope at the European Southern Observatory's La Silla facility in Chile and a telescope at Perth Observatory in Australia. Over the next 2 weeks, they monitored the event continuously, catching a brief spike in brightness lasting approximately 12 hours, the signature of a planet. From the characteristics of this spike, astronomers could infer remarkable details about a world they would never see directly. The duration of the spike indicated the planet's mass relative to its star, about 5.5 times the mass of Earth. The timing of the spike within the overall lensing event revealed the planet's orbital distance, between 2 and 4 astronomical units from its host star, placing it in a region that would fall between Mars and Jupiter if it existed in our solar system. The properties of the main lensing event revealed that the host star was a cool red dwarf with about 22% of the Sun's mass, located approximately 21,500 light-years from Earth, near the center of the Milky Way galaxy. With these parameters established, calculating the planet's temperature became straightforward. A low-mass, cool star emits far less energy than the Sun. A planet orbiting such a star at several astronomical units distance receives minimal heating. The weak stellar radiation, combined with the planet's likely lack of internal heat generation, rocky planets cool much faster than gas giants, produces surface temperatures around 50 Kelvin. At this temperature, virtually every substance we encounter in daily life would freeze solid. The planet's surface likely consists of exotic ices, frozen nitrogen, frozen methane, frozen ammonia, frozen carbon dioxide, and frozen water, creating a landscape more alien than any science fiction artist has imagined. Ogle 2000 5BLG 390 LB likely possesses a rocky core, similar to Earth's iron-nickel core, surrounded by a mantle of rock and ice. The planet's mass, 5 times Earth's, places it firmly in the super-Earth category, larger than our world but smaller than gas or ice giants. The exact internal structure depends on the planet's composition. If it formed with a composition similar to Earth's, with substantial rock and metal, its radius might be only 1.5 to 2 times Earth's radius. If it contains significant amounts of ice, accumulated from the icy region of the protoplanetary disk where it likely formed, it might be larger and less dense. The surface of Ogle 2000 5BLG 390 LB presents a scene of frozen desolation. Any atmosphere that might once have existed has likely frozen out and fallen to the surface as snow, creating layered deposits of different ices. Water ice, one of the hardest substances at these temperatures, might form highlands and mountains, sculpted by ancient impacts. Nitrogen ice, softer and more volatile, might fill lowland basins, forming frozen seas. Methane ice and carbon dioxide ice could create colorful patches across the surface, each compound freezing at slightly different temperatures, and thus occupying different ecological niches in this frigid environment. No geological activity currently shapes this world. On Earth, plate tectonics, volcanism, erosion by wind and water, and the freezing and thawing of ice constantly reshape the surface. But Ogle 2000 5BLG 390 LB experiences none of these processes. Its core has long since cooled, shutting down any internal heat engine that might drive tectonic activity. No liquid water exists to cause erosion. The vanishingly thin residual atmosphere, if any remains at all, cannot create meaningful wind. The surface might be ancient and heavily cratered, preserving a record of impacts stretching back billions of years, each impact site marked by rays of excavated ice radiating outward in frozen stillness. Yet the surface need not be completely unchanging. Even at 50 Kelvin, the most volatile ices undergo sublimation, the direct transition from solid to gas without passing through a liquid phase. When the dim light of the planet's red dwarf star strikes the surface at the right angle, it might provide just enough energy to free a few molecules from the ice lattice, allowing them to hover briefly before refreezing elsewhere. Over millions of years, this process could redistribute ices across the surface, creating subtle patterns visible only to instruments capable of resolving features at interstellar distances. The discovery of Ogle 2000 5BLG 390 LB in 2006 marked several milestones in exoplanet science. At the time, it was the smallest and coldest exoplanet discovered beyond our solar system. Previous exoplanet discoveries had primarily found hot Jupiters or other massive planets orbiting close to their stars, worlds easier to detect but less representative of planetary diversity. OGLE 2000 5BLG 390 LB demonstrated that microlensing could detect smaller, colder worlds that other techniques missed, opening a new window into planetary population studies. The planet's mass and orbital distance also made it significant for theories of planet formation. At 5.5 Earth masses, it falls into a mass range that was poorly represented in exoplanet discoveries at the time. This intermediate size, larger than Earth but much smaller than Neptune, represents a key transition zone in planetary formation theory. Planets in this mass range might form as rocky worlds with thick atmospheres, or as ice-rich worlds with smaller rocky cores. Understanding which formation pathway produces planets like OGLE 2000 5BLG 390 LB helps constrain models of how planetary systems evolve. The planet's location near the center of the Milky Way, some 21,500 light-years distant, makes it one of the most distant confirmed planets known. This distance means that the light carrying information about the microlensing event left the planet's vicinity around 19,500 BCE, during Earth's last ice age, when humans still lived in small hunter-gatherer bands. The photons that revealed this planet's existence traveled across the galaxy for more than 20,000 years before finally arriving at telescopes on Earth, preserving in their patterns of brightness the signature of a distant, frozen world. The planet is unlikely to host life as we understand it. Temperatures of 50 Kelvin are far too cold for liquid water, the universal solvent that makes life's chemistry possible on Earth. Even the most extreme extremophile organisms on Earth, bacteria living in Antarctic ice or in frozen soil in Siberia, require temperatures well above 50 Kelvin to maintain metabolic activity. The complete absence of liquid water, combined with the likely lack of any energy source to drive metabolism, makes biological activity on OGLE 2000 5BLG 390 LB's surface essentially impossible. Yet the planet teaches valuable lessons about planetary diversity and the range of conditions planets can experience. It demonstrates that planets can form and persist in the outer reaches of planetary systems, far from their stars, surviving for billions of years in frozen isolation. It shows that not all rocky planets resemble Earth. Some exist in temperature regimes so extreme they bear little resemblance to anything in our experience. And it suggests that the galaxy contains countless such worlds, frozen and distant, orbiting dim red dwarf stars that comprise the majority of stellar population. Since OGLE 2000 5BLG 390 LB's discovery, astronomers have found other cold super-Earths through microlensing surveys. Each discovery adds to our statistical understanding of how common such worlds are and how they fit into the broader picture of planetary system architecture. These frozen worlds likely outnumber the more easily detected hot Jupiters by a significant margin, representing a major component of the galaxy's planetary population that remains largely unexplored. The planet's nickname, Hoth, references the ice planet that appears in The Empire Strikes Back, the second film in the original Star Wars trilogy. The fictional Hoth features prominent in scenes where the Rebel Alliance establishes a secret base, protecting themselves from the planet's harsh cold within massive ice caverns. While OGLE 2000 5BLG 390 LB shares the fictional planet's frozen nature, it experiences temperatures far colder than anything depicted in the film. The real Hoth represents extremes that would freeze not just water and atmosphere, but the very gases we typically think of as permanent. Nitrogen, methane, carbon dioxide all lie frozen on its surface. Ogle 2000 5BLG 390 LB orbits its red dwarf star every 10 Earth years, following a path that keeps it perpetually distant from its feeble source of light and heat. The star itself appears from the planet's surface as little more than a bright star, perhaps casting faint shadows across the frozen landscape, but providing no meaningful warmth. The sky above this world would be black even during daytime, filled with the cold light of distant stars, the subtle glow of the Milky Way's core visible despite the intervening dust and gas that obscures it from Earth. This planet stands as a monument to the diversity of worlds the universe has produced. From the searing heat of planets orbiting close to massive stars, to the frozen darkness of worlds like Ogle 2000 5BLG 390 LB, orbiting faint red dwarfs at great distances. Planets span the full range of temperatures thermodynamics allows. Each world tells a story of formation, evolution, and survival under conditions unique to its location and history. Ogle 2000 5BLG 390 LB's story is one of cold, deep, abiding cold that has shaped every aspect of its existence since the moment it coalesced from the protoplanetary disk billions of years ago, and will continue shaping it for billions of years to come. Uranus and Neptune, the ice giants of our solar system. While exoplanets dominate discussions of extreme planetary environments, our own solar system hosts worlds of remarkable coldness. Beyond the orbit of Saturn lie two enormous planets whose temperatures and compositions place them among the coldest large bodies in the Sun's family. These ice giants, Uranus and Neptune, experience frigid conditions that make them valuable laboratories for understanding planetary atmospheres under extreme cold. Uranus holds a unique distinction in our solar system. It is the coldest planet, despite not being the most distant from the Sun. At the top of its cloud layers, temperatures plunge to approximately 49 Kelvin, or minus 224 degrees Celsius, or minus 371 degrees Fahrenheit. This temperature surpasses even Neptune's coldness, despite Neptune orbiting more than 10 astronomical units farther from the Sun than Uranus. This paradox has puzzled astronomers for decades and continues to drive research into the ice giant's internal structure and energy balance. Neptune, orbiting at an average distance of 30 astronomical units from the Sun, 30 times farther than Earth, receives only 1/900th of the solar energy that warms our world. At this distance, the Sun appears as little more than a very bright star, insufficient to provide meaningful heating. Yet Neptune's upper atmosphere maintains temperatures around 55 Kelvin, or minus 218 degrees Celsius, slightly warmer than Uranus despite receiving less sunlight. The explanation lies in internal heat. Neptune emits approximately 2.6 times more energy than it receives from the Sun, the highest ratio of any planet. This internal heat, generated by the slow gravitational contraction of the planet's interior, keeps Neptune's atmosphere slightly warmer than Uranus's. Uranus, in contrast, emits far less internal heat than the other giant planets, only about 1/10 as much as Neptune, despite having similar mass and composition. This anomalously low heat emission remains one of the great unsolved mysteries of planetary science. Various theories attempt to explain it. Perhaps Uranus's extreme axial tilt, 98 degrees, meaning the planet essentially rolls on its side as it orbits the Sun, affected its thermal evolution in some way. Perhaps a massive impact during its formation disrupted its internal structure, interfering with normal heat transport processes. Or perhaps its interior has stratified in an unusual way, preventing heat from the deep interior from reaching the surface efficiently. The ice giants' compositions differ substantially from those of the gas giants Jupiter and Saturn. While all 4 planets contain hydrogen and helium as major constituents, Uranus and Neptune have much higher proportions of heavier materials. Their interiors likely consist of a small rocky core surrounded by a deep layer of hot, compressed ices. Not ice in the familiar sense of frozen water, but a hot, dense fluid composed of water, methane, and ammonia under extreme pressure. This ice layer behaves more like a supercritical fluid, neither quite liquid nor quite gas, occupying pressures and temperatures where the distinction between phases breaks down. Above this ice layer lies the atmosphere proper, thousands of kilometers of hydrogen, helium, and methane gas that gradually thins with altitude until it merges with space. Methane in the upper atmosphere absorbs red light preferentially, giving both ice giants their distinctive blue color. Uranus appears as a pale cyan orb, nearly featureless in visible light, with only subtle cloud bands visible in the most detailed images. Neptune displays a richer blue hue, with more visible atmospheric features including large dark spots analogous to Jupiter's Great Red Spot. Neptune's atmosphere, despite its distance from the sun and cold temperatures, exhibits remarkably vigorous weather. The Voyager 2 spacecraft, which remains the only mission to have visited either ice giant, discovered winds on Neptune exceeding 1,500 miles per hour, the fastest winds measured on any planet in the solar system. These supersonic winds race around the planet in jet streams, driven by the combination of Neptune's internal heat and its rapid 16-hour rotation period. The energy source driving such violent weather on such a cold, distant world remains incompletely understood. In contrast, Uranus's atmosphere appears calm and nearly featureless. The lack of visible cloud bands and storms may relate to its low internal heat emission, which provides less energy to drive atmospheric dynamics. Alternatively, Uranus's extreme axial tilt creates unusual seasonal patterns unlike those of any other planet. Over the course of its 84-year orbital period, each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. This extreme seasonality might affect atmospheric circulation in ways that suppress the formation of prominent cloud features. Both ice giants host extensive systems of rings and moons. Uranus possesses 13 known rings, generally dark and narrow, composed primarily of water ice mixed with dark organic compounds. These rings likely formed from fragmented moons destroyed by impacts or tidal forces. Neptune's ring system consists of 5 main rings, some incomplete arcs rather than complete circles, also composed primarily of ice particles darkened by radiation. The moons of the ice giants experience even colder conditions than their host planets. Triton, Neptune's largest moon, holds the distinction of being the coldest large object in the solar system whose surface temperature has been directly measured. Voyager 2 found surface temperatures on Triton around 38 Kelvin, or minus 235 degrees Celsius. At this temperature, nitrogen ice covers much of the surface, and nitrogen geysers, plumes of vaporized nitrogen erupting from beneath the surface, create dark streaks across frozen plains. Triton likely originated as a Kuiper belt object captured by Neptune's gravity, its high inclination and retrograde orbit suggesting a violent capture event that probably disrupted any previous moon system Neptune might have possessed. Miranda, one of Uranus's 5 major moons, displays some of the most geologically complex terrain in the solar system despite its small size, only 470 kilometers in diameter. Its surface features enormous canyons, parallel ridges, and regions of sharply contrasting terrain types, suggesting a violent past possibly involving tidal heating when the moon moved in a more elliptical orbit. Surface temperatures on Miranda hover around 60 to 70 Kelvin, cold enough that water ice behaves as rigid as rock, allowing steep cliffs and deep canyons to persist over geological time. The ice giants' atmospheres host exotic clouds composed of compounds that would be gases on Earth. Methane ice likely forms clouds in their upper atmospheres. Deeper down, where temperatures and pressures increase, hydrogen sulfide might form clouds, giving the planets a faint smell of rotten eggs if we could somehow sniff their atmospheres. Deeper still, where pressures reach thousands of times Earth's atmospheric pressure, ammonia and water might form high-pressure ice phases or exist as supercritical fluids. Recent research has suggested that both ice giants might experience precipitation unlike anything on Earth. At certain depths, where temperatures and pressures reach critical values, theoretical models propose that methane or carbon might be compressed into diamond crystals that slowly sink through the fluid interior. These diamond rains would be transient. At even greater depths, extreme temperatures would break down the diamond crystals back into carbon and hydrogen. But in the intermediate zone, according to these models, diamonds might form, grow, and fall like snow, creating an industry's worth of gems in the invisible depths of the planet. The magnetic fields of the ice giants reveal another oddity. Unlike Earth's magnetic field, which is approximately aligned with the rotation axis and generated in the liquid iron core, or Jupiter's field, which is also roughly aligned and generated in its metallic hydrogen layer, the magnetic fields of both Uranus and Neptune are tilted at large angles to their rotation axes and offset from the planet's centers. Uranus's magnetic field is tilted 59 degrees from its rotation axis, while Neptune's is tilted 47 degrees. This unusual geometry suggests that their magnetic fields are generated in a different region than Earth's or Jupiter's, perhaps in the relatively shallow ice layer rather than deep in the core. These tilted, offset magnetic fields create complex magnetospheres, the regions of space dominated by planetary magnetic fields rather than the solar wind. Particles trapped in these magnetospheres experience constantly changing magnetic environments as the planets rotate, leading to unusual auroral displays. Voyager 2 detected both ultraviolet and infrared auroras on both ice giants, though their properties differed from the more familiar auroras on Earth or Jupiter due to the unusual magnetic field geometries. The ice giants represent an important class of planets that may be common throughout the galaxy. While Jupiter and Saturn analogs likely exist around many stars, ice giants, intermediate in size between terrestrial planets and gas giants, may actually be even more abundant. Statistical analyses of exoplanet discoveries suggest that planets in the mass range of Uranus and Neptune, 15 to 20 Earth masses, occur frequently in other planetary systems. Understanding our own ice giants, therefore, provides crucial context for interpreting observations of similar worlds orbiting distant stars. Future missions to the ice giants remain high priorities in planetary science. NASA and ESA have both studied concepts for dedicated missions to Uranus or Neptune, potentially including orbiters and atmospheric probes. Such missions would revolutionize our understanding of these cold, distant worlds, measuring their compositions in detail, studying their weather patterns over extended periods, mapping their magnetic fields, and examining their ring systems and moons. The knowledge gained would extend far beyond our solar system, informing models of ice giant exoplanets throughout the galaxy. The ice giants remind us that even in our own cosmic backyard, worlds exist that challenge our terrestrial intuitions. Planets where atmospheres span thousands of kilometers, yet contain no solid surface to stand on. Where winds exceed the speed of sound. Where exotic ices flow like water under crushing pressures. where temperatures barely reach above absolute zero, yet internal processes still shape the worlds above. These planets, formed billions of years ago in the outer reaches of the protoplanetary disk that gave birth to all the sun's children, have maintained their cold vigil for all of recorded history and will continue to do so for billions of years to come. Distant blue sentinels marking the outer boundary of our solar system's planetary realm. Pluto and trans-Neptunian objects, frozen worlds at the solar system's edge. Beyond Neptune lies a realm of cold unlike anything closer to the sun, a region where temperatures plunge so low that substances we think of as permanent gases freeze solid and fall as snow, where sunlight arrives so weakened that noontime brightness barely exceeds Earth's twilight, where worlds drift in eternal darkness interrupted only by the faint glow of distant stars. This is the domain of the trans-Neptunian objects, icy bodies that populate the Kuiper belt and scattered disk, relics from the solar system's formation that have remained frozen in time for over 4 billion years. At the forefront of this frozen frontier stands Pluto, the most famous dwarf planet and the first trans-Neptunian object to be explored up close by a spacecraft. Orbiting at an average distance of 39.5 astronomical units from the Sun, Pluto experiences surface temperatures ranging from -360 to -400 degrees Fahrenheit, or -218 to -240 degrees Celsius, or 38 to 55 Kelvin. These temperatures place Pluto among the coldest large bodies in our solar system, cold enough that substances we consider gases on Earth exist only as frozen solids on its distant surface. NASA's New Horizons spacecraft transformed our understanding of Pluto when it flew past the dwarf planet on July 14, 2015, coming within 7,800 miles of its surface. Before this encounter, Pluto remained a fuzzy blur even in the most powerful telescopes, its surface features completely unknown. What New Horizons revealed astounded the scientific community. Not the dead, cratered world many expected, but an active, geologically complex world with diverse landscapes, shaped by processes operating at temperatures barely above absolute zero. The surface of Pluto displays remarkable variety despite its frigid conditions. The most prominent feature, informally named Tombo Regio, but often called the Heart, spans 1,600 kilometers across and consists of 2 distinct lobes. The western lobe, Sputnik Planitia, forms an enormous basin filled with nitrogen, methane, and carbon monoxide ices, substances that are gases on Earth but freeze solid at Pluto's temperatures. These volatile ices are soft compared to water ice, which at Pluto's temperature becomes as hard and rigid as granite. Sputnik Planitia exhibits one of the most remarkable features found anywhere in the solar system: convection cells visible from space. The plane is divided into irregular polygonal shapes, each measuring tens of kilometers across, formed by slow convection of nitrogen ice. Internal heat from Pluto's interior, though minimal, provides just enough energy to warm the bottom of the ice layer slightly. This warmed ice becomes less dense and rises, while cooler, denser ice at the surface sinks, creating a churning pattern similar to boiling water, though operating over timescales of millions of years rather than seconds. The surface of Sputnik Planitia shows no impact craters, indicating it is geologically young, less than 10 million years old, and actively resurfacing through this slow convection process. Surrounding Sputnik Planitia rise mountains of water ice, some reaching heights of 3,400 meters. These mountains were one of the most surprising discoveries of the New Horizons mission. Water ice at Pluto's temperature is rigid enough to support such towering peaks, unlike nitrogen ice, which would flow under its own weight. The mountains likely formed through tectonic processes, possibly driven by the freezing of a subsurface ocean. Water expands as it freezes, and the gradual solidification of such an ocean would create enormous stresses in Pluto's crust, pushing up mountain ranges and creating the complex terrain observed across the dwarf planet's surface. Evidence for a subsurface ocean beneath Pluto's frozen crust comes from several sources. The presence of extensional faults and fractures across the surface suggests internal stresses consistent with an expanding crust. Theoretical models of Pluto's thermal evolution indicate that radioactive decay in the rocky core could generate enough heat to maintain liquid water beneath hundreds of kilometers of ice, despite surface temperatures of -230 degrees Celsius. The reorientation of Sputnik Planitia toward Charon, Pluto's largest moon, points to a mass concentration that models suggest could be explained by a thinner crust or denser subsurface material, possibly including a liquid ocean. If Pluto harbors a subsurface ocean, it would not be alone among trans-Neptunian objects. Several other bodies in the outer solar system show evidence of internal oceans, suggesting that liquid water, the essential ingredient for life as we know it, may be common in the frozen reaches beyond Neptune. The heat needed to maintain such oceans comes from radioactive decay and tidal heating, processes that can continue for billions of years, even in the absence of significant solar heating. Pluto's atmosphere presents another remarkable feature of this cold world. Despite surface temperatures that would freeze almost every gas, Pluto maintains a thin atmosphere composed primarily of nitrogen, with traces of methane and carbon monoxide. The atmospheric pressure at Pluto's surface measures only about 10 microbars, 100,000 times less than Earth's surface pressure. But this tenuous envelope extends remarkably high, reaching altitudes of 1,600 kilometers. The atmosphere exists because of sublimation, the direct transition of ice to gas without passing through a liquid phase. When sunlight warms certain regions of Pluto's surface, nitrogen ice sublimes and enters the atmosphere. This process is most efficient where the surface is darkest and absorbs more solar energy. The sublimed nitrogen then condenses elsewhere on the planet, creating a slow global circulation pattern that redistributes ice across the surface over thousands of years. This sublimation cycle drives Pluto's weather, such as it is, creating winds that can reach 20 miles per hour despite the incredibly thin atmosphere. New Horizons discovered more than 20 distinct haze layers in Pluto's atmosphere, stretching from the surface to altitudes exceeding 150 kilometers. These hazes form when ultraviolet radiation from the sun breaks apart methane molecules high in the atmosphere. The fragments recombine into complex organic molecules called tholins, which appear as bluish haze when backlit by the sun. Tholins eventually settle onto Pluto's surface, contributing to the reddish-brown coloration seen in many regions, particularly around the equator. The atmosphere exhibits a steep temperature gradient, with temperatures increasing from -397 degrees Fahrenheit at the surface to -280 degrees Fahrenheit at altitudes of just 10 kilometers. This temperature inversion, where temperature increases with altitude rather than decreasing, arises from methane in the upper atmosphere absorbing solar radiation. The inversion stabilizes the atmosphere against convection, creating distinct layers rather than the turbulent mixing seen in Earth's lower atmosphere. Pluto's atmosphere undergoes dramatic seasonal changes as the dwarf planet moves through its 248-year orbit. When Pluto approaches perihelion, its closest point to the sun, increased solar heating causes more ice to sublime, thickening the atmosphere. As Pluto recedes toward aphelion, its farthest point, the atmosphere cools and much of it freezes back onto the surface. Models predict that during Pluto's coldest periods, perhaps 95% or more of the atmosphere might collapse, leaving only a vanishingly thin residual envelope. This atmospheric collapse occurs over timescales of decades, a rapid change by planetary standards. Pluto's largest moon, Charon, orbits just 19,600 kilometers from the dwarf planet, so close that Pluto and Charon are often considered a binary system rather than a planet and moon. The two objects orbit a common center of mass that lies between them rather than inside either body. Charon is approximately half Pluto's diameter and 1/8 its mass, making it proportionally the largest moon relative to its parent body in the solar system. Charon experiences even colder temperatures than Pluto because it lacks significant volatile ices on its surface. With an average surface temperature around -220 degrees Celsius, or 53 Kelvin, Charon's surface consists primarily of water ice mixed with various frozen compounds. The moon displays a surprising diversity of terrain despite its small size and cold temperatures. The northern hemisphere features relatively smooth plains, while the southern hemisphere shows more cratered, ancient terrain. One of Charon's most striking features is its dark red northern polar cap, formed from tholins. These organic molecules originate on Pluto. Methane gas that escapes from Pluto's atmosphere can reach Charon, where it freezes onto the cold polar regions during winter. When spring arrives decades later, sunlight breaks down the methane, creating tholins that stain the ice. This process of atmospheric transfer between Pluto and Charon represents one of the few known examples of material exchange between planetary bodies. Charon also shows evidence of past geological activity despite its frigid surface. Enormous canyons stretch across its surface, some over 7 kilometers deep and hundreds of kilometers long, 4 times the scale of the Grand Canyon. These canyons likely formed when an internal ocean froze and expanded, fracturing the crust. The lack of large impact basins suggests that Charon underwent significant resurfacing relatively recently in geological terms, perhaps within the last few billion years. Beyond Pluto and Charon lie countless other trans-Neptunian objects, each experiencing similar or even colder temperatures. Eris, another dwarf planet orbiting at an average distance of 68 astronomical units from the Sun, maintains surface temperatures around 30 to 40 Kelvin, even colder than Pluto. At these temperatures, even nitrogen freezes solid, creating a surface covered in nitrogen and methane ices that never sublime under normal conditions. Makemake, orbiting at about 45 astronomical units, has an estimated surface temperature around 30 Kelvin as well. Observations suggest its surface consists primarily of methane ice with traces of ethane and possibly nitrogen. Unlike Pluto, Makemake shows no evidence of an atmosphere, perhaps because its lower temperature prevents sufficient sublimation of surface ices. Haumea, a rapidly rotating dwarf planet with an elongated shape, maintains temperatures around 50 Kelvin at its average distance of 43 astronomical units. Its unusual shape results from rapid rotation. Haumea completes one rotation every 3.9 hours, the fastest spin of any large object in the solar system. This rapid rotation has deformed the dwarf planet into an ellipsoid, with dimensions approximately 2,000 by 1,500 by 1,000 kilometers. The trans-Neptunian region also hosts numerous smaller objects, many of which remain undiscovered due to their small size and enormous distance. These bodies, ranging from a few kilometers to hundreds of kilometers in diameter, all experience extreme cold. They represent pristine samples of the material from which the solar system formed, preserved in deep freeze for over 4 billion years. Their compositions reflect the conditions in the outer protoplanetary disk where they formed, rich in water ice, methane, ammonia, and other volatile compounds that were too warm to condense in the inner solar system. Some trans-Neptunian objects follow highly elliptical orbits that carry them far beyond the Kuiper belt into the scattered disk region. These objects can reach distances exceeding 1,000 astronomical units at aphelion, where temperatures drop to within a few degrees of absolute zero. At such distances, the Sun appears as merely a bright star, providing negligible warmth. Any volatile ices present would remain frozen solid indefinitely, never subliming, creating surfaces that are among the most pristine and unaltered in the solar system. The study of trans-Neptunian objects reveals the outer limits of planetary temperatures in bound orbits around the Sun. While not as cold as interstellar space or rogue planets, these frozen worlds demonstrate how matter behaves at temperatures approaching absolute zero, where quantum effects become increasingly important and familiar processes of geology and atmosphere yield to exotic physics governed by near-total stillness at the molecular level. Rogue planets, wanderers in the cosmic dark. Beyond the realm of planets orbiting stars lies perhaps the coldest category of planetary bodies, rogue planets, also called free-floating planets or nomad planets. These worlds drift through interstellar space without any star to provide warmth, experiencing temperatures determined solely by their residual formation heat and the cosmic microwave background radiation. They represent the ultimate expression of planetary coldness, existing in an environment where the already minimal heating from a distant star is entirely absent. Rogue planets form through several possible mechanisms. Some may have formed in orbit around stars, but were later ejected through gravitational interactions with other planets or passing stars. Computer simulations of planetary system formation suggest that such ejections are common, particularly in young systems where multiple large planets compete for orbital stability. A close encounter between two gas giants, for instance, could fling one of them into interstellar space, while the other settles into a more stable orbit. Other rogue planets might form directly in interstellar space through the collapse of gas clouds too small to ignite fusion and become stars. This process would resemble star formation, but on a smaller scale, producing objects with planetary masses, but without any parent star. The boundary between such objects and brown dwarfs, failed stars, becomes somewhat arbitrary, defined primarily by mass rather than formation mechanism. Detecting rogue planets presents extraordinary challenges. Without a star to orbit, they cannot be found through the radial velocity method or transit observations. They emit no visible light of their own, making direct imaging nearly impossible except for very young, massive planets still radiating heat from their formation. Instead, astronomers rely primarily on gravitational microlensing, the same technique used to discover Ogle 2000 5BLG 390 Lb, where a rogue planet's gravity briefly magnifies the light of a background star as it passes in front of it. Several candidates for rogue planets have been identified through microlensing surveys. Some studies suggest that rogue planets may be extremely common, possibly outnumbering stars in our galaxy. Surface processes and atmospheres on the coldest worlds. Despite their frigid temperatures, cold planets are not geologically dead. Various processes reshape their surfaces, drive atmospheric cycles, and create diverse landscapes, all operating under the constraints of extreme cold that fundamentally alter how familiar processes manifest. Ice tectonics replace the plate tectonics and volcanism common on warmer worlds. On cold planets, water ice behaves as rock does on Earth, forming rigid crusts that can fracture and deform. Nitrogen ice, methane ice, and other volatile ices flow more readily, creating glaciers that move under their own weight. These glaciers carve valleys, create smooth planes, and transport material across planetary surfaces over geological timescales. Pluto's surface demonstrates these processes vividly. Nitrogen ice glaciers flow from Sputnik Planische's basin into surrounding terrain, creating features resembling Earth's ice streams, though operating on vastly different temperature and compositional regimes. The convective cells in Sputnik Planitia represent another form of surface activity driven by temperature differences of just a few degrees, sufficient to create density variations that drive convection over millions of years. Cryovolcanism, or ice volcanism, might occur on some cold worlds. Rather than erupting molten rock like Earth's volcanoes, cryovolcanoes would erupt mixtures of water, ammonia, methane, and other volatiles in liquid or gaseous form. The source of heat for such eruptions remains uncertain, perhaps tidal heating from moons or nearby planets, perhaps radioactive decay in the interior, or perhaps phase transitions as subsurface ices crystallize into denser forms, releasing latent heat. Several features on icy moons and dwarf planets have been interpreted as potential cryovolcanoes. Wright Mons and Pickard Mons on Pluto, two large mountains with summit depressions, resemble shield volcanoes formed by repeated eruptions. Triton exhibits what appear to be frozen lava flows and geyser-like eruptions of nitrogen gas. Enceladus, Saturn's moon, has active geysers spraying water vapor and ice particles from fractures near its south pole, demonstrating that geological activity persists even at temperatures below -180 degrees Celsius. Sublimation cycles drive atmospheric processes on cold worlds with tenuous atmospheres. When surface ice absorbs enough solar energy or heat from the planet's interior, it sublimes directly to gas without melting. This gas enters the atmosphere, increasing pressure and potentially driving winds. When the gas later condenses elsewhere on the surface, it deposits fresh ice, gradually redistributing material and modifying the surface appearance over time. Pluto's atmosphere demonstrates this cycle clearly. Nitrogen ice in Sputnik Planitia sublimes during Pluto's day and condenses on the night side or in permanently shadowed regions. Over Pluto's 248-year orbit, the distribution of ice shifts as different regions experience varying amounts of sunlight. Computer models suggest that most of Pluto's nitrogen ice eventually accumulates in Sputnik Planitia because of its low elevation and latitude, creating a cold trap where ice remains more stable than elsewhere on the surface. Impact cratering continues even on the coldest worlds, though at reduced rates compared to the early solar system. Asteroids and comets occasionally strike these distant bodies, excavating craters and ejecting material into space or across the surface. At extreme cold, the mechanical properties of icy surfaces change. They become more rigid, shattering rather than flowing under impact stresses. This creates crater morphologies different from those on warmer bodies, with sharper rims and less slumping of crater walls. Space weathering also affects cold planet surfaces, though differently than on warmer bodies or airless worlds closer to the sun. Cosmic rays and solar ultraviolet radiation break down complex organic molecules on the surface, creating tholins and other compounds that darken the surface over time. Charged particles from the solar wind and cosmic rays create chemical changes in surface ices, converting some molecules into others, and potentially creating a thin layer of modified material distinct from the pristine ice beneath. Cold planet atmospheres exhibit unique phenomena. Temperature inversions, where temperature increases with altitude, are common because methane or other greenhouse gases absorb solar ultraviolet radiation in the upper atmosphere. These inversions suppress vertical mixing, creating distinct layers that can persist for long periods. Haze layers form when photochemistry in the upper atmosphere creates aerosols that settle slowly through the thin atmosphere. On the coldest planets with atmospheres, the lower atmosphere might be saturated with vapor at the dew point or frost point for various substances. Clouds of nitrogen ice, methane ice, or other volatiles could form, creating weather systems operating at temperatures below -200 degrees Celsius. Such clouds would look similar to Earth's cirrus clouds, thin, wispy formations composed of ice crystals, but made of exotic ices instead of water. Atmospheric escape represents another important process. Atoms and molecules in the upper atmosphere occasionally gain enough energy to exceed the planet's escape velocity and fly off into space. This process, called Jean's escape, occurs more rapidly for lighter molecules and on smaller planets with weaker gravity. Over billions of years, atmospheric escape can strip away significant fractions of a planet's atmosphere, particularly if the planet lacks a strong magnetic field to shield its atmosphere from the solar wind. Triton's atmosphere displays active geyser-like eruptions despite surface temperatures around 38 Kelvin. These eruptions occur when solar heating penetrates through transparent nitrogen ice and warms darker material beneath. The warmed nitrogen vaporizes, building up pressure until it breaks through the surface layer, erupting in plumes that carry dark particles hundreds of kilometers into the thin atmosphere. These particles eventually settle back to the surface, creating dark streaks visible in images taken by Voyager 2. The coldest planets also experience seasons, though on vastly different timescales than Earth's familiar cycle. Pluto's extreme axial tilt creates situations where each pole alternately experiences decades of continuous sunlight followed by decades of darkness. This extreme seasonal cycle affects atmospheric pressure, ice distribution, and surface appearance in ways still being analyzed from New Horizons data. Models predict that Pluto's atmosphere might partially collapse and freeze out near aphelion, only to revive as the dwarf planet approaches the Sun again. Understanding surface processes on cold planets requires rethinking familiar geological and atmospheric concepts. Water acts as rock. Nitrogen acts as water. Methane acts like carbon dioxide does on Earth. Each substance occupies a different ecological niche determined by temperature, pressure, and composition. The resulting landscapes and atmospheric phenomena, while following the same physical laws that govern Earth's surface, produce outcomes different from anything in terrestrial experience. The search for life in extreme cold. The coldest planets seem intuitively inhospitable to life. Temperatures approaching absolute zero, lack of liquid water on surfaces, minimal energy sources. These factors appear to preclude biological activity. Yet life on Earth has repeatedly surprised us with its ability to survive and even thrive in extreme environments. This has led some astrobiologists to wonder whether life might find ways to exist even in the frozen reaches of the outer solar system and beyond. Life as we know it requires several fundamental ingredients. Liquid water serves as the universal solvent, facilitating chemical reactions necessary for metabolism and reproduction. Energy sources drive these reactions, whether from sunlight through photosynthesis, chemical energy from redox reactions, or heat from hydrothermal vents. Organic molecules provide the building blocks for biological structures. Liquid water remains the most fundamental requirement. No known form of life can function without it in some capacity. On the surfaces of the coldest planets, liquid water cannot exist. Temperatures far below the freezing point ensure that any water remains frozen solid, as hard as granite. Surface life seems impossible under these conditions. But beneath the frozen crusts of these worlds, conditions might be more favorable. Internal heat from radioactive decay, tidal heating from moons or nearby planets, or residual formation heat could maintain liquid water oceans beneath kilometers of ice. Pluto, Triton, and several other trans-Neptunian objects show evidence suggesting subsurface oceans. These oceans would be completely dark, never seeing sunlight, but analogous environments on Earth support thriving ecosystems. Deep-sea hydrothermal vents on Earth's ocean floor host communities of bacteria, archaea, and even complex organisms like tube worms and clams, all surviving without photosynthesis. Chemical energy from reactions between hot vent fluids and seawater drives these ecosystems, proving that life can exist without sunlight. If similar hydrothermal systems exist in subsurface oceans on cold planets, they could potentially support microbial life. The chemistry would differ, water reacting with a silicate seafloor, possibly modified by ammonia or other antifreeze compounds dissolved in the ocean. But the fundamental principle, chemical energy driving metabolic reactions, could operate even in this frozen environment. The challenges for such life would be formidable. Energy availability would be limited compared to sunlight-driven ecosystems on Earth. The ocean would be completely isolated from the surface, except possibly through occasional cryovolcanic eruptions, limiting exchange of materials with the outside environment. The extreme pressure at the bottom of a deep subsurface ocean would require any organisms to adapt to conditions we can barely recreate in laboratories. Yet Earth's deepest oceans harbor life adapted to enormous pressures exceeding 1,000 atmospheres. Bacteria have been found in rock fractures kilometers beneath Earth's surface, surviving on chemical energy from reactions between rock and water. Some microorganisms can remain viable after being frozen for hundreds of thousands of years. Life's tenacity suggests that if conditions in subsurface oceans permit even minimal metabolism, life might find a way to establish itself. Detecting such life would be extraordinarily challenging. The ice shells covering subsurface oceans might be dozens or hundreds of kilometers thick, far beyond our current drilling capabilities. Landing on these worlds and searching for biosignatures would require technologies not yet developed. Instead, astronomers search for indirect evidence, chemical signatures in plumes of material ejected from the interior, as occurs on Enceladus, or spectroscopic detection of molecules that might indicate biological activity. The discovery of organic molecules on Pluto's surface, while not evidence of life, demonstrates that complex carbon chemistry occurs even in the coldest environments. Tholins and other organic compounds form through photochemistry and radiation chemistry, creating a rich inventory of carbon-based molecules. If subsurface oceans exist and occasionally communicate with the surface through geological processes, an idea supported by the presence of young surface features on some icy worlds. These organic molecules might provide raw materials for any hypothetical life in the ocean below. Some scientists have speculated about alternative biochemistries that might function at extreme cold. On Earth, all known life uses water as its solvent and operates at temperatures above the freezing point of water. But could life exist using liquid methane or liquid ammonia as its solvent instead? These liquids exist at much lower temperatures than water. Methane remains liquid from 91 to 112 Kelvin at 1 atmosphere pressure, while ammonia remains liquid from 195 to 240 Kelvin. Life using such alternative biochemistries would be radically different from Earth life. Chemical reactions proceed much more slowly at lower temperatures, potentially requiring organisms to live on geological timescales rather than the rapid metabolic cycles familiar on Earth. The types of molecules stable in liquid methane or ammonia differ from those stable in water, necessitating different biochemical pathways. No evidence suggests such life exists, but its theoretical possibility prevents us from completely dismissing cold worlds as potential habitats. Titan, Saturn's largest moon, hosts liquid methane lakes and seas on its surface at temperatures around 94 Kelvin. While not technically a planet, Titan represents perhaps the best place in the solar system to search for alternative biochemistry. The Cassini mission detected complex organic molecules in Titan's atmosphere and on its surface, created by photochemistry acting on methane and nitrogen. Future missions might search for evidence of metabolism in the lakes and seas, looking for chemical disequilibria that might indicate life using liquid methane as its medium. The coldest exoplanets are unlikely to harbor life on their surfaces or in their atmospheres. Temperatures of 50 Kelvin or below preclude any chemistry we would recognize as metabolic. But some of these worlds might possess moons experiencing tidal heating, creating environments where subsurface oceans could exist. The detection of such moons orbiting cold exoplanets remains beyond current capabilities, but represents a goal for future observatories. The search for life on cold planets ultimately tests the boundaries of biology. How cold can life tolerate? Can life exist without sunlight? Can metabolism occur on timescales of millions of years rather than seconds? Can alternative solvents support biochemistry? Each question pushes our understanding of what life is and how it functions. Even if we never find life on the coldest worlds, the search expands our conception of where and how life might arise in the universe. Future exploration and observation. The coldest planets, both within our solar system and orbiting distant stars, represent frontiers for future exploration. New telescopes, spacecraft missions, and detection techniques will revolutionize our understanding of these frozen worlds over the coming decades. The James Webb Space Telescope has already begun transforming exoplanet science. Its unprecedented infrared sensitivity allows direct detection of cold planets like Epsilon Indi Ab and detailed atmospheric characterization of worlds like WD 1856 plus 534. Future observations will expand the catalog of directly imaged cold exoplanets, potentially discovering even colder worlds and measuring their atmospheric compositions with precision impossible from ground-based telescopes. The Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, will conduct extensive microlensing surveys. These surveys will detect thousands of new exoplanets, including cold planets at wide orbital separations and potentially numerous rogue planets. Statistical analyses of these discoveries will constrain how common different types of cold planets are and how planetary system architecture relates to stellar properties. Ground-based telescopes continue to improve through adaptive optics and interferometry. The extremely large telescope, under construction in Chile, will have a mirror 39 meters in diameter, more than twice the size of any existing optical infrared telescope. This enormous collecting area will enable direct imaging of planets around nearby stars and detailed spectroscopy of planetary atmospheres, including cold planets that remain beyond current detection limits. Within our solar system, several proposed missions target the coldest worlds. NASA has studied concepts for an orbiter mission to Pluto, which would return to the dwarf planet to conduct extended observations of its atmosphere, surface, and seasonal changes. Such a mission could measure atmospheric composition throughout Pluto's year, map the surface at much higher resolution than New Horizons achieved during its brief flyby, and potentially detect subsurface oceans through precision gravity measurements. Missions to Uranus or Neptune represent high priorities in planetary science. These ice giants remain poorly understood. Voyager 2's brief flybys in the 1980s provided our only close-up views. An orbiter mission could spend years studying their atmospheres, magnetic fields, ring systems, and moons. Atmospheric probes could descend into their atmospheres, directly sampling composition and measuring conditions at different depths. Such missions would reveal how ice giants work, providing crucial data for understanding similar exoplanets throughout the galaxy. The search for rogue planets will benefit from upcoming wide-field infrared surveys. The coldest rogue planets emit most of their radiation in the infrared, making them invisible to optical telescopes, but detectable with infrared instruments. Large infrared space telescopes could potentially detect rogue planets in our cosmic neighborhood through direct imaging, revealing their temperatures, sizes, and possibly even atmospheric properties if they're warm enough and close enough. Theoretical work continues to refine models of cold planet atmospheres and interiors. Computer simulations predict how different gases behave at extreme cold, how clouds form and dissipate, how heat transports through planetary interiors. These models guide observations by predicting what features to look for and what measurements to make. As observations improve, they test and constrain these models, creating an iterative process that progressively deepens our understanding. Laboratory experiments complement observations and theory. Scientists recreate conditions found on cold planets in terrestrial laboratories, measuring properties of exotic ices, studying chemical reactions at extreme cold, testing how organic molecules behave in frozen environments. These experiments provide data impossible to obtain through astronomical observations, filling gaps in our knowledge and revealing phenomena that might occur on real planets. The ultimate goal remains sending spacecraft to explore these worlds up close. While missions to exoplanets lie beyond current or near-future technology, every world in our solar system remains potentially accessible to robotic explorers. Future generations might see spacecraft landing on Pluto, drilling through the ice shells of trans-Neptunian objects to reach subsurface oceans, or deploying floating platforms in Titan's methane lakes. Each mission would transform our understanding, just as New Horizons revealed Pluto's unexpected complexity. Conclusion: eternal stillness in the frozen depths. As our journey through the coldest realms of the cosmos draws to a close, we find ourselves contemplating worlds that exist at the very boundaries of temperature, where molecular motion slows to its minimum, where exotic ices form landscapes unlike anything in human experience, where the faint light of distant stars struggles to pierce the eternal cold. These frozen worlds, from the exoplanet WD 1856 plus 534b orbiting its white dwarf host, to the frigid super-Earth Ogle 2005 BLG 390 LB drifting in the outer reaches of its planetary system, to the ice giants Uranus and Neptune in our own cosmic backyard, to distant Pluto with its nitrogen glaciers and thin atmosphere, to rogue planets wandering alone through interstellar space. All demonstrate the remarkable diversity of planetary environments nature has produced. They show us that planets are not merely variations on Earth's theme, but span a vast range of conditions, each type revealing different aspects of how physics and chemistry manifest under extreme circumstances. The study of cold planets expands our understanding of planetary processes. We learn how atmospheres behave when temperatures drop so low that major constituents freeze out. We discover how geological processes operate when water ice becomes as rigid as rock and nitrogen ice flows like water. We observe how weather patterns form in the thinnest atmospheres at temperatures barely above absolute zero. Each discovery adds to the comprehensive picture of how planets work across all possible conditions. These worlds also inspire wonder and contemplation. The realization that a planet might drift alone through the galaxy for billions of years, experiencing cold beyond anything we can truly imagine. Lit only by the faint glow of distant stars, evokes a profound sense of cosmic isolation and endurance. The knowledge that beneath Pluto's frozen surface might exist an ocean, dark and deep, holding more water than all of Earth's oceans combined, suggests mysteries still awaiting discovery, even in our own solar system. As you prepare to rest, consider the stillness of these frozen worlds. Their surfaces, shaped over billions of years, remain largely unchanging from one millennium to the next. Their atmospheres, when they exist at all, drift in slow circulation patterns driven by temperature differences of just a few degrees. Their interiors, cooled over eons, maintain whatever warmth remains from formation or from the patient decay of radioactive elements. In this stillness, we find a different kind of beauty, not the dramatic violence of volcanic eruptions or the churning chaos of gas giant atmospheres, but the serene permanence of ice held at temperatures where change occurs only on geological timescales. These worlds exist in a state approaching cosmic equilibrium, their energies minimized, their forms stabilized, their futures stretching across billions of years largely unchanged. Let your thoughts drift like nitrogen snow settling onto Pluto's frozen plains. Let your breathing slow to match the patient cycle of sublimation and condensation that redistributes ice across these distant worlds over millions of years. Let the deep cold of these planets carry you into rest, knowing that in the vast cosmos, stillness and motion both have their place, and in the frozen reaches beyond the warm embrace of nearby stars, planets endure in eternal patience. If you found this exploration of the coldest planets fascinating, please consider liking this video, leaving a comment about which frozen world intrigued you most, and subscribing to Alien Nature for Sleep for more journeys through the extraordinary environments our universe has created. Share this video with anyone who finds comfort in contemplating the cosmos, and join our community of curious minds exploring the alien landscapes that exist beyond our warm blue world. Thank you for joining tonight's journey to the coldest corners of existence. May your dreams be as serene as the frozen landscapes we've visited together, and may you find peace in the knowledge that even in the deepest cold, the universe continues its patient work, creating, preserving, and enduring across the endless expanse of space and time. Sleep well, knowing that while we rest, these frozen worlds continue their silent orbits through the darkness, monuments to the incredible diversity of planetary nature, witnesses to the profound cold that governs the outer reaches of existence, reminders that in the cosmos, every extreme has its place, and every world, no matter how cold, tells a story worth knowing. Good night,